Welcome to Unit 10 of Chemistry, Acids, Bases, and Solutions. What are solutions? So this is going to be the overarching topic of our whole unit here. We're going to talk about some specific types of solutions when we get into acids and bases, but let's discuss what a solution is first. A solution is a homogeneous mixture where the particles are evenly mixed but not chemically combined. So we discussed very early on in the course that a homogeneous mixture is one that you can't tell that there's different particles in it. It looks uniformly mixed. But in this solution, we are not chemically combining anything. So there's no chemical reactions occurring when you dissolve something into a solution. Each particle retains its original properties. For example, powdered lemonade is an example of a solution, and sugar particles here are dissolved, but can be physically separated through evaporation. So they are dissolved into the water here, but they're not chemically reacting with the water. Every solution has two parts: a solute, which is the substance that's being dissolved, which often we recognize as a solid, but it doesn't have to be a solid. Sometimes there are liquid solutes or gas solutes. But in our powdered lemonade example, we did have a solid solute. And then the solvent is the substance that's doing the dissolving, which is often a liquid. And so in our example here, the water is the solvent and the powdered lemonade is the solute. Now, colloids often get confused with solutions because they look similar. Colloids are heterogeneous mixtures that do not settle out, so they can be confused with solutions. Milk, for example, is a colloid. And so you might assume, just looking at milk, it looks like it's a uniform mixture and it doesn't settle out on its own very easily. And so it looks like it could be a solution. Because the particles in a colloid, however, are larger than those in a solution, they disperse light. And this is known as the Tyndall effect. So this is a way to differentiate between solutions and colloids. The particles in a solution are so small that the light is not going to be dispersed when it passes into it, and so it will pass right through the other side. A colloid, however, because it has the larger particles, is going to show a scattering of light, and you will see the beam of light in that mixture. And so that's a way to differentiate between solutions and colloids, even though they look very similar. So as we discussed, solutes don't always have to be solids, and two liquids can actually make a solution together. If they combine to form a uniform solution, we call those miscible liquids. For example, 5% vinegar is made of acetic acid and water. So if you went and found a bottle of vinegar on the shelf in your house, it would likely say that it's 3% or 5%, and that is 3 or 5% acetic acid, and the rest of it is water. But it's not distinguishable. The acetic acid and water are not distinguishable from each other. It's a uniform solution. And so we say that those two liquids are miscible. Immiscible solutions, however, are formed from two liquids that separate into different layers and they do not mix. So oil and water is an example of that. If a solution does mix together, if we're talking about a solute that is able to dissolve into a solvent and create a solution, the solution has a particular concentration. The concentration of a solution describes how much of the solute is dissolved into the solvent. and it's measured in a unit called molarity. Molarity is calculated, abbreviated with a capital M, by the way, but it's calculated by moles of solute divided by liters of solution. So which solution here has the greatest molarity? And this will also be the solution with the highest concentration. So if we look at all of these flasks of liquid, the one that is going to have the most moles of solute is probably this darkest one here, because these are all going to be less concentrated than this. These are going to have less solute in them if it was a clear solvent, which we would assume that maybe it is. So this is going to have the highest concentration and the highest calculated molarity. The concentration of a solution can also be calculated as percent by mass or percent by volume. So percent by mass is just what it sounds like, the mass of the solute divided by the mass of the whole total solution. So this is very similar to how we would calculate any percent, the mass of a part over the mass of the whole times 100. And percent by volume is similar, volume of the solute divided by volume of the total solution times 100. So just remember when you are looking at these that this is not the mass of the solvent, it's the mass of the total solution. And same thing with this one, volume of the total solution. So let's do a percent by mass example problem. IV bags used to deliver fluids to hospital patients must be at a specific saline or NaCl concentration. If 9 grams of NaCl is dissolved in 1,000 grams of water, what is the concentration of the saline solution? Let's use our percent by mass formula. And we know that 9 grams is our mass of solute. 1,000 grams of water is our mass of solvent. And so we're going to add those together to get our mass of solution. In reality, sometimes that's a lower mass than it can be calculated to be, but for our purposes, we're going to use the ideal solution here, that 1,000 grams of water plus 9 grams of salt gives us our total solution mass. And so we have 9 grams of solute divided by 1,009 grams of solution. And we divide that out and multiply by 100. We get 0.89%, or rounding to 0.9% for sig figs. Now the volume of a liquid solution can change based on its temperature, but its mass does not. So we know that liquids have more space between the particles than solids do. So the volume of a liquid is able to change a little bit more because there is more space in between those particles. And so temperature can affect the movement of the molecules a little bit more than in a solid. So it's sometimes more accurate to measure the solution in molality rather than in molarity. So molality accounts for the mass of the solution rather than using the total volume of the solution, which is a little bit more susceptible to changes based on temperature. So molality would be moles of solute divided by kilograms of solvent. Instead of liters, which is a little bit more changeable, kilograms of solvent would give us our molality. We still do a lot of our calculations in molarity. Just know that this is actually a little bit more accurate and used some of the time for solutions. So, example here, if 30.7 grams of copper nitrate are dissolved in 700 grams of water, what is the molality of the solution? So our first step is to convert our grams of copper nitrate into moles, since that's our solute. And then we're going to divide by kilograms of solvent, which is our water. And so we're going to convert our 700 into kilograms. So starting here with our molar mass, we're going to take 30.7 grams of copper nitrate, use the molar mass of copper nitrate, and gives us 0.16 moles of copper nitrate. And we're going to divide that by 0.7 kilograms. So we are converting our 700 grams. And that's going to give us 0.23 moles per kilogram, which would be the molality of that solution. In summary, solutions are homogeneous mixtures composed of solutes dissolved into solvents. They do not disperse light. The concentration of a solution can be represented in molarity or molality, which use moles, or percentage. So far, we've been discussing one substance dissolving in another in very middle school-like terms. We're not discussing the chemistry, really, of what's happening here. So let's get into some more detail. Well, the process of dissolving is actually called solvation in chemistry terms. And what's happening here is when a solute is added to a solvent, the solvent particles surround the solute particles, breaking them apart. So we have water molecules here in our solvent, and we have sodium chloride, NaCl, as our solute in this image. And you can see that because water is a polar molecule, part of it is partially negatively charged, and that negatively charged side of the water molecule is attracted to the positively charged sodium ion. And so they surround the sodium ion, while the positive side of the hydrogen of the water molecules is attracted to the negatively charged chlorine ion. And so those surround the chlorine ions, and that is how the solute ends up being broken apart, because those solvent particles are surrounding them and pulling those charged particles away from each other. Solvation in water is known as hydration. So we've discussed water a lot as a solvent, but it's not the only solvent by any means, but we do have a specific term for it. The extent to which the solute dissolves is based on whether it has a similar polarity to the solvent. So we were looking at a polar solvent here and an ionic compound, which does have different charged particles in it. And so the polarity of the solvent and the polarity of the solute, and whether those match, is what allows a solute to either dissolve well or to not dissolve. So polar solvents dissolve polar solutes, and nonpolar solvents dissolve nonpolar solutes. And we generally describe that by saying like dissolves like. So here's a fun example. Chocolate and chewing gum both have an oil base, which is nonpolar. Oil is a nonpolar molecule. When chewing the chocolate at the same time as the gum, which I'm sure you've never done regularly, but the oil in the chocolate will dissolve the gum base and change the consistency of the gum. So if you don't believe me, go try it. It's a fun little experiment. And that's because both of these, even though we're not really dissolving a solid solute in a liquid solvent, they are able to dissolve each other because they are both nonpolar and like dissolves like. So what factors affect the rate of solvation? So now we know that solvation is taking place. How quickly does it happen? Well, the rate of solvation can increase if collisions between the solvent and solute particles occur more frequently. We're trying to get those solvent particles around the solute particles, and the faster they can access those solute particles, the quicker the solute will dissolve. So this can happen in 3 ways. Increasing the temperature. This increases the kinetic energy of the particles. Usually we're increasing the temperature of the solvent so that the particles in the solvent are moving more quickly and therefore able to break the solute apart more rapidly because they have more kinetic energy, and so they're bumping into those solute particles more frequently. Stirring or agitation increases, again, the collisions between the solute and the solvent, and so if we are physically stirring the solution, the solvent particles are able to bump into those solute particles more frequently. And we can also increase the surface area of the solute. The solute particles are then more easily accessed by the solvent particles. So rather than a large chunk of solute, if we broke it into a powder or into smaller pieces, those solvent particles would be able to access the solute molecules more quickly, and solvation would increase. So you generally know this, I'm sure, from liquids and solutions that you've dealt with in your life. You probably know that it is easier to stir powdered cocoa mix into hot water rather than cold because the water particles have more kinetic energy, and so they're able to bump into those cocoa mix molecules more frequently. So how many particles can a solution actually contain? So now we've discussed the process of it. What about the amount? So how much solute can we really put into a solution? Well, an unsaturated solution contains less solute than a saturated one. So here we're working our way up from less solute to more solute. And this unsaturated solution has less solute than it actually is physically able to contain. So more solute would be able to be dissolved in this unsaturated solution because it still has a lot of solvent particles that have not surrounded solute. And so they're able to be accessed, and therefore we could add more solute to this solution. In a saturated solution, the rate of solvation is equal to the rate of recrystallization. So no more solute can be dissolved. So if you think of this on a molecular level, all of the solvent particles have surrounded the solute particles. And now some of the solute particles are going to bump into each other again and begin to form crystals. So this is sort of equal here in that the rate of solvation or dissolving the solute is equal to the formation of the solute. And so this solution is as full of solute as possible. No more solute can be dissolved in this solution, and we call that saturated. Then we have this unusual arrangement in a supersaturated solution. So a supersaturated solution contains more solute than is theoretically possible. And this is achieved by dissolving while heating the solution and then letting it cool. So saturation points, as we'll learn in a second here, are based on temperature. The hotter the temperature, the more solute we can dissolve into a solution, and the higher the saturation point. If a solution was heated and more solute was added and then it was cooled back down, for the temperature, the current temperature, this solution would actually have more solute in it than is theoretically possible. And sometimes that looks like crystals then developing on the sides or the bottom of the solution. And we'll get into a little bit more about how that works when you do your lab. So what are solubility curves? So this is where we recognize how temperature plays a part in the saturation point of a solution. So the saturation point is dependent on both temperature and pressure of the solution. And a solubility curve shows how much solute can be dissolved in a given amount of solvent for a variety of temperatures. Solubility of solids generally increases with temperature, as we've been discussing, but the solubility of gases in liquids generally decreases with increasing temperature. So here are examples of solubility curves. You can see solubility curves for lots of different solids here. And on the left-hand side, we have the solubility, which is the grams of whatever the salt is that we're testing in 100 grams of water. And then across the bottom, we have increasing temperature. So you can see that if we look at sodium chloride here, as the temperature of the solution or solvent increases, the amount of sodium chloride that can be dissolved, or the saturation point of that solution, is increasing with increasing temperature. The cesium sulfate is one of the unique different types of solids here that actually decreases in its solubility with increasing temperature. But most of these solid salts are increasing in their solubility as the temperature increases. Gases, however, with increasing temperature, decrease their ability to dissolve. And that's because as the temperature of the solution increases, it's bumping into those gas particles more rapidly. And those gases, because they're less dense, are then able to actually break out of the solution more easily. So they are less soluble in high temperatures because they want to be released from the solution as those high kinetic energy particles are bumping into them. So in summary, the solubility of a solute depends on its polarity compared to that of the solvent, as well as the temperature and pressure of the solvent. When the maximum amount of solute is dissolved, the solution is said to be saturated. What are electrolytes? This is probably a term that you've heard before in your everyday life. Ionic compounds are known as electrolytes because when the ions dissociate in a solution, the solution conducts an electrical current. So these are basically solutions of ionic compounds that have already dissolved and the ions have dissociated. And so those ions are now able to conduct electricity, and so we call those electrolytes. Some molecular compounds, remember molecular compounds are covalently bonded, are also electrolytes. The strength of an electrolyte, in other words, how much current it can produce, depends on how many ions the solute produces in the water. So sports drinks contain ions such as sodium, calcium, potassium, and magnesium. These drinks are often advertised as high in electrolytes, which can replenish minerals lost during strenuous exercise. And this is necessary because sweat is not just made of water, it also contains lots of minerals and ions, and so replenishing with electrolytes helps to replenish those minerals rather than just replenishing with water. Most molecular compounds dissolve in solvents, but do not dissociate into ions. These solutions are known as non-electrolytes. So here, sucrose or sugar is a molecular compound, so it's covalently bonded. Although water molecules surround the polar sucrose molecules, they do not dissociate into ions, so the solution cannot conduct electricity. So see how this ionic compound completely dissociates, and that allows electricity to be well conducted through the solution. But this one does not fully dissociate and so does not conduct electricity well. What are colligative properties? Well, many physical properties of solutions are not based on the type of solute, so sugar versus salt, but on the number of solute particles in the solution. And these are called colligative properties. Colligative meaning relating to the collection of particles in the solution. Which type of solution has more solute particles? An electrolyte or a non-electrolyte? And the answer is going to be an electrolyte because it dissociates into at least 2 ions. And some ionic compounds dissociate into more than 2 ions, which would give them even stronger colligative properties because there are multiple particles that are being released from that compound. So there are 4 major colligative properties. First, a decrease in vapor pressure. So again, we're talking here about colligative properties or properties that are based on the amount of solute particles. So in non-volatile compounds or non-volatile solutes, which means that they don't readily evaporate, an increase in solute can cause a decrease in vapor pressure. And the reason is because since the solvent particles are occupied or basically surrounding the solute particles and attracted to them, there are fewer solvent particles that are able to vaporize at the surface of the solution. And so this keeps the amount of vapor being produced and therefore vapor pressure lower. Next is an increase in boiling point. Because fewer solvent molecules are able to escape, because just as we said here for vapor pressure, they're basically occupied and surrounding those solute particles. So fewer solvent molecules are escaping, and therefore the temperature of the solution must be increased in order to cause vaporization, in order to force them to escape being surrounding those solute particles. The temperature of the solution needs to be increased in order to add enough kinetic energy to cause them to want to leave those solute particles and escape into the air. You've probably seen this in the kitchen. Salt is often added to water when cooking pasta, and the reason for this is because it causes the water to boil at a higher temperature. So it requires more heat then in order for the pot to boil, and so the pasta then cooks faster when it's added. You may have heard that adding salt to your water helps it boil more quickly, and that is not true. It actually takes longer for the water to boil. If enough salt is added, it does take a significant amount of salt to actually make that change. But it makes the water boil more slowly, but therefore it's at a higher temperature when you add the pasta. So the pasta actually cooks faster, but the water boils more slowly. Third property caused by colligative properties is a decrease in freezing point. So picturing this in a molecular setting here, the solute particles are surrounded by the solvent, and the solvent molecules then are not able to form their typical structure, typical solid structure. So the solute particles are interfering with the solvent's intermolecular forces, and therefore it causes a decrease in the freezing point because the solvent particles are not able to form the attraction required for them to become a solid. Number 4 is an increase in osmotic pressure. And that's a fancy term, but I'll explain it here. So solute draws water across a semi-permeable membrane. You may have learned about this in biology class already. Higher concentrations of solute cause more water to move, increasing osmotic pressure. So the way that I've always explained this in biology is that solute sucks. The more solute there is in one side or one solution or one side of this tube, for example, the more water is going to be drawn into it, or it's going to suck water from a different location into that concentrated area. So here we have a semi-permeable membrane in between these two sides. We call this a U-tube. And the semi-permeable membrane allows small water particles to move, but prevents the movement of these larger solute particles. The holes here, or the filter, is too small, and so these larger solute particles are not able to pass through, but the water is. Polar water molecules are attracted to the solute particles. So the water that was on this side is actually being drawn across to help balance out that concentrated solution on this side. And so that these water molecules can surround each of these individual solute particles. And that causes the osmotic pressure to rise on the side of the tube with the highest solute concentration. So here we have a greater osmotic pressure as the water is being drawn into this side of the tube because it has the highest solute concentration. So in summary, electrolytes dissociate into ions in solution. The concentration of ions causes colligative properties such as the lowering of vapor pressure and freezing point, and the increase in boiling point and osmotic pressure. So we've been discussing ionic compounds like all of the ionic compounds are soluble, and that's not the case. In fact, not all ionic compounds are soluble. Some of them are not able to dissociate in water. Solubility rules help chemists predict how compounds will interact in aqueous solutions. So if we're discussing a couple of aqueous solutions and you wanted to pour one into the other, solubility rules will help to predict what will happen so that you don't have to test it all the time in possibly a dangerous situation. If two aqueous solutions combine and one of the products is insoluble, a precipitate will form. So these solutions here all contain insoluble precipitates. You can see all of those different colored precipitates as a result of mixing two aqueous solutions. So two clear solutions which don't refract light. They would look clear to you in some form. When you pour them together, a precipitate or a solid form, insoluble solute, would form in these situations. And so these are three different precipitates that you can see from a variety of interactions. So what are the solubility rules? Well, first of all, it's important to know that you don't need to memorize these. So we'll go through practicing some of these solubility rules, but this chart does not need to be memorized, so don't get overwhelmed by it. And I'll help you figure out how to read it as we go. So the best way to do this is simply to practice. Let's start with, is sodium carbonate soluble? So first we're going to find our polyatomic ion here for carbonate. Carbonate is right here. So it is an insoluble compound. However, it will be soluble, these are the exceptions over here, if it's attached to lithium, sodium, potassium, rubidium, or cesium, and ammonia. So because it has sodium here and sodium here, that will be a soluble compound. So yes, if we were able to put that into an aqueous solution, it would dissociate and dissolve. Is barium sulfate soluble? So our first step here is to find our sulfates here. This is under a soluble compound, so sulfates are soluble unless they contain any of these elements. So barium sulfate, because it includes a barium ion, is not going to be soluble because this is an exception. Is strontium nitrate soluble? So we're going to find the nitrates here. They are soluble. No exceptions here, so strontium nitrate will be soluble. Is magnesium hydroxide soluble? Hydroxides are down here, and these are the exceptions. None of those are magnesium, so that will be an insoluble compound here. Will be no for our solubility. Last question for practice. Will mixing lithium sulfate and calcium nitrate form a precipitate? So if any of the products of this reaction are insoluble, then they will form a precipitate, and then because they will come out of solution. So our first step is to predict the products of this reaction. Lithium sulfate and calcium nitrate will form a double replacement reaction. And so the two products will be lithium nitrate and calcium sulfate. So lithium nitrate here is a soluble compound, no exceptions, so that one would be soluble. Calcium sulfate, here are sulfates, so that's soluble, except calcium is here, so that will not be a soluble compound. So yes, it will form a precipitate because the products here will be aqueous lithium nitrate and solid calcium sulfate. Okay, what are spectator ions? So since aqueous solutions involve dissociated ions, these reactions can be written with ions rather than compounds. So it's basically like breaking these two compounds apart like we just did, including our separate ions of lithium and sulfate and calcium and nitrate instead of the compounds themselves. So here's another example. If we had sodium chloride added to silver nitrate, and that formed sodium nitrate and silver chloride, we could write this reaction, which has 3 aqueous solutions here and 1 solid product. We could write it in its dissociated ions. So that would be sodium ions and chlorine ions, silver ions, and we keep this polyatomic nitrate ion as a whole unit. And then our products would be a sodium ion, a nitrate ion, and silver chloride, which is our solid. So all of these aqueous ions would be written separately. Our solid compound remains as a solid compound because it is not dissociated into ions. A spectator ion is one that does not participate in the reaction, so it's found on both sides of the arrow. So just like a spectator of a sport is someone that's not participating in the sport, a spectator ion is not participating in the reaction. And so it's not going to be part of this insoluble precipitate. It is going to be found on both sides of our reaction here in ionic form. So if we look again at all of our ions and our silver chloride precipitate, these 4 are our spectator ions because they are found on both sides of the equation. Chlorine and silver are not found in ion form on this product side of the reaction, so they are not spectator ions. These 4 are going to be our spectator ions. And so how is a net ionic equation written? Well, this is going to be the result of writing out all of those spectator ions. So a net ionic equation just includes the ions involved in the reaction without the spectator ions. So if we start here with our same reaction and we eliminate all of our spectator ions, our net ionic equation for this reaction would be Ag plus Cl minus yields AgCl. And so these are the only ions and compounds that are participating in the reaction, and we're going to eliminate the spectator ions. So now you can get a clear idea of what's actually happening in this solution. As a side note here, generally the positive ion is written first for clarity, but you don't have to do it that way. That's just generally the way that it's done. So this is the precipitate of silver chloride. Spectator ions are still dissociated in this aqueous solution around it. So these are the ions that have reacted, have created this solid precipitate, and then all of those other spectator ions are still in solution. So in summary, solubility rules are used to predict how ionic compounds will interact in aqueous solutions. Spectator ions do not participate in aqueous reactions, but other ions can form precipitates. In the next section of this unit, we're going to start discussing very specific types of solutions. And those types are acids and bases, which you're probably a little familiar with already. Acids have a sour taste, are electrolytes. In other words, they dissociate in solution to be able to conduct electricity. They have a low pH value, and we'll get into the pH scale in a little bit here, but just for now, know that they have a low pH value, which is less than 7 on the pH scale. They turn blue litmus paper red. Litmus paper is an indicator, and we'll talk more about indicators as well in this unit. And so when blue litmus paper comes in the presence of an acid, it indicates that by turning red. Citrus fruit contains citric acid and ascorbic acid, and so those are acidic fruits, which gives them that sour taste. Vinegar also contains acetic acid, and we use that for cooking and cleaning. Bases, on the other hand, are slippery, have a bitter taste, are also electrolytes. They have a high pH value of above 7, and they turn red litmus paper blue. So again, another indicator here. Red litmus paper will turn blue to indicate that it's in the presence of a base. Bases are also called alkaline sometimes. That's a word we use to describe them. And soap and oven cleaner are both examples of bases that you probably have around your house. So how exactly do we define acids and bases? Well, the properties of acids and bases have been known since the time of ancient Greece. But modern chemistry now uses molecular models to define them. So just like you might have some idea of acids and bases and their properties or how we might use them from everyday life, ancient Greeks did know quite a bit about acids and bases, but they did not understand the molecular chemistry of them. And so some scientists in more modern days have used molecular models to explain more clearly the properties and attributes of acids and bases. The first one was Arrhenius, and the Arrhenius model says that acids produce hydrogen ions, or H+ ions, in aqueous solutions, while bases produce OH- ions, or hydroxide ions. So for example, when dissolved in water, hydrochloric acid dissociates into H plus and Cl minus. NaOH, sodium hydroxide, dissociates into Na plus and OH minus. So we would consider HCl to be an acid because it produces H plus ions. And we'd consider NaOH to be a base because it produces OH minus ions when it's in an aqueous solution in water. And like I said, this model is named after Svante Arrhenius, a Swedish chemist that proposed it in 1883. But it does have some issues. For example, the Arrhenius model doesn't account for all acids and bases. Ammonia, for example, is a base, but it does not contain an OH group. So here's the molecular model for ammonia. It has all the properties of a base, but it doesn't have an OH group. So other scientists have adjusted that model to account for some of these exceptions. So let's look at a more updated model, and that's called the Bronsted-Lowry model. It says that acids are H plus donors and bases are H plus acceptors. So for example, if we're talking about hydrochloric acid here and we're mixing it in water, yes, it does produce an H plus ion, but that ion is actually given to the water molecules. And so that is an H plus donor, and that would make the water here a base because it is receiving that H plus, or I know I've been saying H plus, but generally we also consider that a proton. So that would mean that the hydrochloric acid here is an acid because it donates a hydrogen ion, and the water would be a base because it receives the hydrogen ion. Water can actually act as an acid or a base, and that makes it known as an amphoteric substance because it can work in either way, depending on which chemicals it's being mixed with. So, like I said, throughout this unit, we might be using the terms H plus ion and proton interchangeably. So I was calling this an H plus ion or H plus, but generally we do talk about it as a proton when we're discussing acids and bases. And that's because an H plus ion is simply a hydrogen atom that has lost an electron. And since it only has one proton in the nucleus, when it loses this electron, it's just one proton here. So those are synonymous terms. H plus ion and proton are exactly the same. So what are acid-base pairs? Well, when an acid donates a proton or hydrogen ion to a base, the resulting ions on the product side are called conjugates. And a conjugate acid-base pair is a pair of substances that differ by only one proton. So let's look at an example here. If we use our same reaction, hydrochloric acid plus water yields this is called a hydronium ion and a chlorine ion. This is going to be our acid because it is donating a proton. The water in this case is acting as a base. The hydronium ion is going to be our conjugate acid because it has received a proton from the hydrochloric acid. So it actually now has an extra proton that it can donate in another reaction or in the reverse reaction. And so we now call it a conjugate acid. And the chlorine here has lost a proton, and it can then become a proton acceptor. And so that makes it a conjugate base because it may accept a proton later. And since proton receivers are the bases, we now call this a conjugate base. So bases convert into conjugate acids, and acids convert into conjugate bases. And then we call these two compounds here, or ions, a conjugate pair. So this would be a conjugate pair here, and then hydrochloric acid and its chlorine ion would be another conjugate pair. Acid-base pairs arise because after receiving an H+ ion or hydrogen ion, a base can now donate it in the reverse reaction. So I just mentioned that. That is why it's known as a conjugate acid. So it's sort of a temporary acid until it donates that hydrogen ion again. So generally your reaction will look like an acid plus a base yields a conjugate base and a conjugate acid, with our acid and conjugate base being a conjugate pair, and the base and the conjugate acid being a conjugate pair as well, with our double arrow here to represent the fact that this reaction could occur in either direction. So let's practice identifying the following conjugate acid and base pairs. This is going to be our hydrogen donating compound. So this is our acid, which means that water will be our base in this reaction. Our nitrate ion is going to be the conjugate base then, because this acid removed a proton and now is able to receive it again later. So that's going to be our conjugate base, which makes the hydronium ion our conjugate acid. So looking at this, I want you to try to figure out the conjugate, the acid, the base, the conjugate acid, and the conjugate base in this reaction. So pause the video, try it, and then come back and check your answers. Okay, so this is acetic acid. This is our acid. It has a hydrogen ion at the end, a hydrogen atom that's going to be donated. So that's our acid. Water will be our base, our hydrogen receiver here, and that makes this resulting ion our conjugate base, and the hydronium ion our conjugate acid. So in summary, acids and bases are both electrolytes, but with different properties. They are defined by either the ions they form in solution or by whether they donate or receive protons. When acids donate a proton, they become a conjugate base. Okay, let's talk about naming acids and bases. I know that we've looked at this a long time ago when we were talking about compounds, but let's look at it more closely again, since we're going to be focusing heavily on acids and bases in this unit. And it's important for you to know how to read the names of the compounds as you're answering these questions. So how are binary acids named? We'll start there. Binary acids, bi means two. Binary acids consist of hydrogen and one other element, usually a halogen. And the rule for naming binary acids is that you start with the prefix hydro, and then from the second element, you remove the "ide" suffix and add "ic." So this sounds complicated, but it's really not too bad. So let's take a look at some practice problems. HCl is a binary acid because it has hydrogen and one other element. So we're going to start with the prefix hydro. So we know that this is named hydro something. And then we're going to remove the "ide" from the chloride here. And we're going to change it to "ic." So now we have hydrochloric acid. So not too bad. Think about this one, and then let's check it together. So this should be hydrobromic acid. Bromide changes to bromic. This one is hydrofluoric acid. And then we have hydroiodic acid. So those are our binary acids. There are also oxyacids, which are acids that have oxygen in them. So oxyacids contain hydrogen, oxygen, and a third element, often a nonmetal. The name depends on the ending of the anion, which remember is the second portion of the compound. Rule: if the anion ends in ate, you remove the ate and change the ending to ic. So here we have HNO3, and that contains a nitrate ion here. And so it ends in ate. We're going to remove that ate and we're going to change it to ic. There's no hydro in these, so this is going to just be nitric acid. So this one, we have a carbonate ion here for our anion. So we're going to remove the ate, change it to ic. This is going to be carbonic acid. Rather than carbonate, carbonic acid. Try this one. If we know that our ion here, anion, is perchlorate, then that should be perchloric acid. And our final practice here, if this is a permanganate ion here, that's going to be permanganic acid. So those are our oxyacids. And then we have one more rule. If the anion in your oxyacids ends in ite, you're going to remove the ite and change it to us. So before we were talking about ate in our polyatomic ions here, but if that polyatomic ion ends in ite, you're going to change the ending to us instead of ic. So here's some examples. This is a nitrite ion, and so rather than using ic, we're going to use us here, and this will be nitrous acid. This one, same thing. We've got sulfite, and so that's going to be sulfurous acid. And our final practice, this is phosphite. This is going to become phosphorus acid. Now note here that sulfur and phosphorus are sort of exceptions to these rules. They follow the correct suffix rule, so they do change to the us. But rather than just sulfus acid, the full word of sulfur is used here, so sulfurous acid. And so same thing with phosphorus acid. Rather than phosphus acid, they name the whole thing phosphorus acid. And so those are just two that you're going to have to remember. There's no good reason for it that I know of. It's just easier to say, and so they became exceptions to the rule here. So here's a memory trick for helping you name acids. My ride has hydraulics. So your ride here, if the ending of the binary acid is "ide," then it's going to have hydro added to it and ic as the suffix. I ate something icky. So ate, if your polyatomic ion ends in ate, then you're going to change it to ic. And if your polyatomic ion ends in ite, you're going to change it to us. So this is all for naming acids, and now we'll get into bases, which is significantly easier. The formula for a base begins with a metal or NH4, which is ammonium, and ends with OH. So the rule is that you write the name of the metal or ammonium ion and add hydroxide to the end, which is the OH. So very simple here. We have sodium and then we have a hydroxide ion. This base is sodium hydroxide. This base is going to be potassium hydroxide. And this one here is really the only complicated one, and this is the ammonium ion. So this is ammonium hydroxide. And then barium, here we have 2 hydroxide ions, but that's not going to change our name. So it's still going to be barium hydroxide. Pretty simple. So let's practice naming acids and bases on your own. I'll give you each question and then you try to answer it and we'll check answers together. Here's your first acid. This breaks into a proton or hydrogen ion and nitrite. So this is going to be nitrous acid. Calcium here, and we have hydroxide, so we know that that's a base. It breaks into calcium and 2 hydroxide ions. So that's going to be calcium hydroxide. Here's your next compound. Try to figure this one out on your own and then pause the video if you need to and come back. Okay, this is an acid and it breaks into 3 protons and 1 phosphate ion. Because this is phosphate, we're going to change the suffix to ic and make that phosphoric acid. And so in summary, acids are named by changing the suffix, determined by the anion. Bases are named by using the name of the metal cation and adding the suffix hydroxide. And we generally categorize acids and bases by their strength. So what are strong acids? Strong acids are acids that completely dissociate into hydrogen ions and an anion in an aqueous solution. Now the hydrogen ion is in a hydronium ion, so the H plus here is joining with H2O in the aqueous solution to create a hydronium ion. So an example is hydrochloric acid, which is a strong acid. And so the H and the Cl here completely dissociate with the hydrogen ion then joining the H2O to create hydronium and a negative chlorine ion. So that complete dissociation and the primarily forward reaction here is what causes that to be considered a strong acid. The strong acids are sulfuric acid, hydroiodic acid, hydrobromic acid, nitric acid, hydrochloric acid, and perchloric acid. So sulfuric acid dissociates so that one of these hydrogen ions is going to join with the H2O and then the other one stays with that sulfate. Hydroiodic acid dissociates completely, as does hydrobromic acid, nitric acid, and hydrochloric acid and perchloric acid. So all of these dissociate completely into separate ions, and that's what makes them strong acids. And so rather than memorizing all of these different strong acids, because it is helpful to know the list of them, here's a memory trick. If you remember, so I brought no clean clothes, That will help you remember sulfuric acid, hydroiodic acid, hydrobromic acid, nitric acid, hydrochloric acid, and perchloric acid. Hopefully that'll give you a good way to remember that. What are strong bases then? As you might imagine, strong bases are bases that completely dissociate into their cation and hydroxide. So very similar, but we're using hydroxide ions here because we're discussing bases. These are group 1 hydroxides, as well as calcium, barium, and strontium hydroxides. So all of these are our group 1 hydroxides, and they completely dissociate into their metal ion and the hydroxide ion. And then, as I mentioned, some of the group 2 hydroxides are also considered strong bases: calcium hydroxide, barium hydroxide, and strontium hydroxide. So I don't have a catchy way to remember this. Just remember that your group 1 hydroxides and then these 3 are your strong bases. What are weak acids and bases? Weak acids and bases only partially dissociate in aqueous solutions. The ions produced from these weak solutions can recombine in a reverse reaction. So the equation is written with a double arrow. So here's our example. Acetic acid, for example, is a weak acid. Here's acetic acid. When it is combined in an aqueous solution, some of the acetic acid releases the hydrogen ion and forms the hydronium ion here and the acetic acid anion, but a lot of this acetic acid stays as it is without dissociating. And so this reaction occurs in both directions very regularly. And so it doesn't dissociate completely and fully. And so we consider that to be a weak acid. Similarly, methylamine is a weak base. It begins here with this compound, and when it is placed in an aqueous solution, it dissociates with the hydroxide ion and then this cation. But again, this is a reversible reaction and it does not fully dissociate. So a lot of those molecules are going to remain as they are. And so we're going to consider that a weak base. How is the strength of an acid or a base measured? The pH scale measures the concentration of H+ or hydrogen ions in a solution. And so this is our pH scale here. It ranges from 0 to 14. Neutral solutions, like water, are found at 7. And then acidic solutions are found from 0 to 6, with the stronger acids being found closer to the 0 end and the weaker acids being closer to neutral here. And then our alkaline or basic solutions are found above the 7 neutral mark, and so 8 to 14, with the strong bases being near the end, near 14, and the weak bases being closer to 8. Because the hydrogen ion concentrations are very small quantities, chemists express the value in pH. So the pH scale is really a model to represent the hydrogen ion concentrations in a variety of solutions. So pH stands for the potential of hydrogen, and it's a logarithmic value of the hydrogen ion concentration. So the equation for calculating pH of a solution is pH equals the negative log of the hydrogen ion concentration. So for example, pure water has a hydrogen ion concentration of 1.0 times 10 to the negative 7th. So this is literally how many hydrogen ions can be found in a sample of water. And the pH then is equal to the negative log of the hydrogen ion concentration here. So we plug in 1.0 times 10 to the negative 7th, and that gives us a pH of 7. Therefore, the pH of pure water, which is a neutral solution, is 7.00. And because pH is a logarithmic scale, a pH on the pH scale of 8 is actually 10 times stronger than a pH of 7. So the distance between the solutions on the pH scale is actually a lot more significant than it seems like it is on that scale of 14. Likewise, the pOH scale measures the concentration of hydroxide ions in a solution. And our equation for this is pOH equals the negative log of the OH minus concentration, or hydroxide ion concentration. And the sum of the pH and the pOH values is 14. So we represent that with the equation pH plus pOH is equal to 14. So if we look back at our pH scale, if we had a pH of 1, we would have a pOH that made up the rest of this pH scale. So it would be a pOH of 13. So the pH value and the pOH value are equal to 14, so that they take up this whole pH scale. So in summary, strong acids and bases dissociate completely in solution, while weak ones partially dissociate in reversible reactions. The pH scale measures the strength of an acid using a logarithmic scale. A neutralization reaction is one in which an acid and a base in an aqueous solution react to form an ionic salt and water. So if we have an aqueous acid here and an aqueous base, and we mix those two together, the reaction is going to create an ionic salt and water here. The resulting solution is more neutral than either the acid or the base. So if you picture here that we were putting in an acid, which is low on the pH scale, and a base, which is high on the pH scale, the combination of the two of those is going to bring that solution, the resulting solution, closer to neutral. And that's why we call it a neutralization reaction. So, for example, if we combine hydrochloric acid, which is a strong acid, and sodium hydroxide, which is a strong base, the resulting solution here will include sodium chloride and water. And because it's got more water in this solution, it's going to be much closer to neutral. When a strong acid is mixed with a strong base, stoichiometry can be used to determine how much of a solution is required in a neutralization reaction. So for example, we can calculate what volume of 1.2 molar sodium hydroxide is required to neutralize 0.7 liters of 0.2 molar sulfuric acid. So we have a strong base and we have a strong acid, and so we can use stoichiometry to figure out the neutralization reaction. So first we're going to write and balance the equation. We've got sulfuric acid and sodium hydroxide, 2 moles of sodium hydroxide, and 1 mole of sodium sulfate, and 2 moles of water. And then we're going to use stoichiometry to calculate what volume of this 1.2 molar sodium hydroxide is required to neutralize our sulfuric acid. So we start with the volume of the known substance. Our known substance is sulfuric acid here because we know the volume and we know the molarity. So we're going to start with the volume of the known, which is 0.7 liters. Make sure you are labeling with your substances. And then we're going to use our molarity of the known to convert from volume to moles. And then we'll use the mole ratio from the equation to compare the sulfuric acid and the sodium hydroxide. So 1 mole of sulfuric acid for every 2 moles of sodium hydroxide. And then now we are at our unknown substance. We're going to use the molarity given in the problem here of the unknown substance. And so we have 1.2 moles per 1 liter. We know that because we have 1.2 molarity. So now we know the volume of the sodium hydroxide, our unknown solution, and we just multiply across, divide by the bottom, and we end up with 0.2 liters of sodium hydroxide. So if we had 0.2 liters of sodium hydroxide that was 1.2 molar, that would allow us to neutralize this amount of sulfuric acid. And we do that in a lab setting using something called a titration. A titration is a lab technique that uses a pH indicator. So the pH indicator is mixed into this solution here, and a known concentration of either an acid or a base, which is called the titrant. So the titrant is put in this very tall burette here, which has measurements on it. And we know the concentration of the solution that's in here. And we're going to use that to determine the unknown concentration of another solution, which is called the analyte. So this is our unknown solution here. If it was a base, we would be using an acid in our burette here. And you just slowly drip the titrant, we'll say acid here. We slowly drip the acid into this unknown base solution. And as soon as the pH indicator changes, then you know that you are at the equivalence point, which is where those two substances have neutralized each other. The titrant is slowly added until the indicator in the analyte changes color. So here's another visualization of the process. If we add our acid into the analyte solution here, this is our unknown solution. And then we add some indicators that we know when the solution is at its equivalence point. And then you're going to add a base. Since we've got an acid down here, we need to neutralize it with a base. So you'd add your known solution of base to the top here. And then based on how much of this base was added, you could figure out exactly the concentration of your unknown solution down here. So you release the, it's called a stopcock here. You release the stopcock and let the liquid very slowly drain into the analyte solution. And then you compare your final reading of the titrant with the initial reading so that you know the volume that's been used. And then we go through that stoichiometry process to determine, based on the volume of this known solution, what is the concentration of this unknown solution down here. So that's how titration works. What is a buffer? Sometimes a buffer is added to the analyte in a titration. Analyte, remember, is this bottom solution here. A buffer is a solution that resists pH change when an acid or base is added to it. This makes it easier to identify exactly when an analyte changes color. So we're adding the pH indicator as well as a buffer to try to really make sure that we know exactly when that solution is able to change color, and therefore when it's at its equivalence point. A buffer is made of a weak acid or base and its conjugate. Because a weak reaction is reversible, it can shift equilibrium to accommodate the addition of acidic or alkaline solutions. So it's shifting that reaction either forward or reverse based on whether acid or base has been added to it to try to balance that solution in equilibrium until it's no longer able to do that. In summary, a neutralization reaction occurs when an acid and base react to form a salt and water. Titrations can be used to determine the concentration of an unknown solution, analyte, which is mixed with an indicator and sometimes a buffer.